Welcome to Ask and Learn.
In this problem, we have two containers of air, and we've got a heat engine in between them. And we have this heat engine in between them, and we're extracting work out. So again, like in the previous problem, I said we could have put a heat engine, between, the surroundings and that chamber of compressed air to get work out. So we have heat flowing in from this tank here and flowing out to this tank here, and we have work coming out of the heat engine. And this tank here is a constant volume, and this one here is a constant pressure. So they both contain air. So if we look at this problem, basically just we have the properties, heat capacities for air that we'll need later. There is, did I write? It seems like I didn't write much of this information down and transfer it over from my notes. Let's see here. Yeah, what did I? Guess I wasn't really. I gave up on writing writing stuff down here. So let's see here. What do we have? The constant volume tank has a temperature of uh, TA is 600 Kelvin and TB is 280 Kelvin. And both have MA equals MB equals 40 kilograms. Okay, now we got our information down in there. Now, let's see here. What else are we told? We just determine the maximum work can be produced by the heat engine and the final temperature of the tank, assuming constant specific heats at room temperature. So we have these specific heats. Now, that these are constant is probably not a great approximation, but we'll use it anyway. So if we look at the entropy equation, again we're assuming there's no change in entropy in the heat engine. This is kind of an ideal heat engine. Does it say that actually specifically in the tank? From the time produces what we just heat to load. Well, again, if we're basically looking for the maximum, so we're assuming that this is ideal also. So we know that if we look at this total enclosed system, there's no entropy in or entropy out because again, this is assuming it's all insulated and there's no heat transfer out that isn't going to or from this heat pump. And because it's ideal, we're assuming that the entropy generated in this whole thing is 0. And so that's the change in entropy in the inside here. And that's the change in entropy in the two tanks. And again, we're assuming that the change in entropy in the heat engine is 0. Well, it should, I mean, yeah. This is a steady process, so there's probably there's really some rate of entropy generation in here, but we're gonna internally it's a steady state process. So basically, there's no entropy in or there's no change in rate of entropy. There's no entropy accumulating in here because again we're assuming that it's perfect. That means that we have ideal gas, so we can write our two changes in entropy in terms of change in temperature and change in pressure for the top one, and then in terms of change in temperature and change in pressure for the bottom one. And we do that because the change in volume up here is 0, and the change in pressure down here is 0. So that go away. So now what we see here is we get the mass goes away because it was the same. That's just happened because we had the same mass of air in both tanks. So what we get is the natural log of T2 whatever the temperature is of, what we're looking for is the temperature of, at this point, we're looking for the temperature of all of this stuff as it equilibrates. So T2, and again, I should index these things with a 1, over TA1, the natural log of that, plus the ratio of the heat capacities times the natural log of T2 over TB1. This thing is K. So we wind up, again, we can, move this over here, take the exponential, both sides, play some games with the math, and we wind up with an equation that looks like this. We have T2 over TA1 times T2 over TB1 to the K, and that equals 1. So we have T2, let's see here, we wind up with, oops, let me see my notes here. Oh yeah, that's what yeah, I was gonna say that doesn't look right. And I missed a K here when I transferred things. Okay, so yeah, so we have T2 is TA1 times TB1 to the K, and all of this to the 1 over K plus 1 power. So we can we know everything here. So we plug everything in and we get 385 Kelvin. So again, this temperature went up, this temperature went down, as what you'd expect. Now we want to look at the heat transfer out of here and the heat transfer into here, and then that will tell us what the idealized work out of here is. So let's see here. We have, again, assuming constant heat capacities. Now we know the change in temperature, so we can just get the heat transfer out was about 6,184 kilojoules. Into here was 4,208 kilojoules. So we know the difference then is the work that came out in the ideal case, and that winds up being close to 2,000 kilojoules would be the maximum amount of work we could get out if we had these two containers initially at these conditions. And again, we assume constant heat capacity, so that's an approximation. If we had not, we would have to do a little more. There'd be more math involved.